Alright, part 3. So we're almost there. So let's take a look at this one here. Look at the inside of this square root. It doesn't look nice, but when you take the derivative, you get negative 2x, and you have an x here, so you may be able to work it out. So let's let u be 4 minus x squared, and then du, let's let it be, that is going to be negative 2x dx. Well, you don't let it be, we calculate it. And now we have here the x dx that it appears here, and we have u inside of the square root. So we can divide or multiply times negative a half actually, and we get exactly what we need, the x dx. And now what we can do is set up our integral with the u's. Now, I'll be careful with the endpoints. I'm not going to touch them at the moment. I'm going to do negative a half. Not going to write anything for the moment. Du, that's going to take care of the yellow. So let me mark it, as I didn't quite do in the part 1, but in part 2 I started, so I'm doing that now. And now I have some sort of endpoints that I will address in 1 second, and then the square root of u. Okay, so that takes care of almost everything but the endpoints, or my interval where I'm integrating. So let's take a look at that. Let me make this a little box here. At x equals 0. That is my left endpoint of my integral, or my left endpoint of the interval where I'm going to be integrating. So that's going to be x equals 0. When you have x equals 0, u will be equal to 4 minus 0 squared, which is going to be 4. So when x is 0, u becomes 4. Since now I'm integrating with respect to u, I don't need my endpoints for x. I need my endpoints for u. So that one becomes 4. At x equals 2, u becomes 4 minus 2 squared, which is going to be 4 minus 4, which is going to give you 0. So that 2 becomes 0, because I don't need my endpoints in terms of x. I need them in terms of u now. Okay, so now we can calculate our integral. So we copy the 1/2, and then we, by the way, we can calculate this definite integral using the first fundamental theorem of calculus. That allows us to calculate the antiderivative of this, or use an antiderivative of this function to evaluate the definite integral. So we calculate the antiderivative, which is going to be u to the 1/2 plus 1, so 3/2, divided by 3/2, or times the reciprocal, which is 2/3. And I am going to evaluate it between 0, no, not between 0, no, between 4 and 0. Yeah, I know I'm going backwards, but that's what it is. So maybe let me continue down here so I don't run out of room. And so that's going to be negative a half. Copy that guy. Evaluate first at 0. Okay, I like that. 0. Minus 2/3. And then evaluate u to 3/2 at 4. What did I write there? I meant 4. There you go. To 3/2. And that gives me, well, 0. And then minus negative, so it becomes positive. The 2 cancel with the 1/2, so I get a 1/3. So the 2 goes away with this 2, the negative goes away with this negative, and I have 2 to the 3/2. So I take the square root of 4 to the 3/2. I take the square root of 4, gives me 2, cube it, gives me 8. So in the end I get 8/3. And that is the answer. Alright. Now some people, you will see that what they will do, that's another option. I don't like it because then you end up messing the endpoints. But some people, what they do is they go to here, they get their antiderivative, and then they take back their substitution. So they get negative 1/3, and then evaluate it. Instead of u, they write their 4 minus x squared to the 3/2, and then they evaluate it at the original endpoints. So you can do that. You can calculate the antiderivative, ignoring your endpoints completely, then you take back your substitution and you use the original endpoints. So you have to be very mindful. If you're going to use the original endpoints, you want x's. If you're going to use the new endpoints, you're going to plug it into the u's. Just be consistent. In any case, this is going to give you the same answer. Not going to calculate it, but gives you the same answer. It's easy, right? I mean, you plug 2, you get 4 minus 4, 0, and then when you plug 0, you get 4 to the 3/2, which is the same thing I had over here. So it's the same thing. You just have to be mindful and be consistent. If you're gonna look at the endpoints for u, you plug it into u, and if you're gonna look at the endpoints for x, you plug it into x. One last one. No, second to last one. So let's look at this one. Now this one, it's not obvious what to do right away. So, but I don't like dealing with square roots, much less if they're in the denominator. So I'm going to call that u. Okay, and then I get du is dx. But I don't see how I can substitute things because apparently I have a mess. So u, and what do you do? Well, the dx is there. Great. But what do I do with that 2x plus 1? That makes no sense whatsoever. But you can kind of fix it because you can go from here and say that x is actually u minus 4. And then you can plug that x into here. And what do you get? You get the integral of 2 times u minus 4, that's x, plus 1. So I did substitute that. Then over the square root of u, I'm plugging the green, and then dx is the yellow, becomes just du. So let's color things out in this integral here. So this u comes from just directly substituting. Now with this x, I plug this in here. You see I have an x there. And then I have my yellow in here. And I substituted everything that I had. The 1 stays the same, the 2 stays the same. So it's all legal, and I can go ahead and try to figure out how to integrate this. Maybe I didn't achieve anything, so let's try to figure it out. So let's distribute this out. So we get 2u, then minus 8 plus 1, so it becomes a minus 7, over the square root of u. Well, that's not too bad, because I can always just treat this one as u to the 1/2 and write this as 2 times u over u to the 1/2. That gives me just 2u to the 1/2 just by copying the exponent of this and subtracting the exponent of this one. So 1 minus 1/2, that's that, and then minus 7u to negative 1/2, because that's going to be u to the 0 minus 1/2, basically, and then du. So now I can just take my antiderivative, so copy the 2, u to the 1/2 plus 1, so 3/2, and then over 3/2 or multiply times the reciprocal is going to be kind of tight here, but I can still fit it. And then minus 7, add 1, so becomes u to the 1/2. I should copy it. And then divided by 1/2, which is the same thing as multiplying times 2. And that becomes 4/3 of x plus 4. Ha, look at that, I forgot my plus c. To the 3/2 minus 14 square root of x plus 4. Just u to the 1/2, plug in u, and then don't forget plus c. And there's your answer. So sometimes you have to do u-substitution and a little more tweaking, a little bit more algebra. So that can happen. One last one for the road, and that is this one. And you say, well, I don't see anything to substitute there. Well, you would be right, but you can always write it as sine of x over cosine of x. And now you see what you want to substitute, because cosine in the bottom doesn't seem to be too nice. So you write cosine du becomes negative sine. And you see that off by a negative sign, but you kind of already have everything you need. Oops, let me color this one. And here I have the cosine. So this one is perfect right here. So I just need to multiply everything times -1. I'm not going to write extra because you can see how that's just going to give me a negative du. And then 1 over u. And that, then, you calculate your antiderivative. Remember, 1 over u, you cannot do power rule for that one. You have to use the logarithm. So you get the natural log of the absolute value of u plus c, which becomes negative natural log of the cosine, absolute value of the cosine, plus c. And then you can use this negative, put it as the exponent. 1 over cosine becomes secant. So natural log of the secant. And that's your answer. Alright, and that's that for today. I went a little over in this video, so we'll see if YouTube allows me to upload it. Alright, that's that.